Good morning and welcome you all to this session of the course on fluid machines. Last class we started the discussion on Francis reaction turbine and we discussed the basic components of the Francis reaction turbine, which is a typically radial inward flow turbine. We have recognized the guide vanes, stay vanes, the runner blades, the purpose of the draft tube and the different terminologies as far as the energy per unit weight, that is the head of the machine is concerned, that the head across the turbine, net head producing the work or the gross head, and how a draft tube increases the net head producing the on the turbine by keeping the turbine at a higher altitude from the tail race level. All these things we discussed. Now, we will analyze the force on the runner blade of a turbine and how expressions for power developed and the blade efficiency, hydraulic efficiency. So, to start with, I will again refer to this figure to know, though this is a very simple figure in a two dimensional plane. Let us consider this figure. Now, the turbine, the runner of the Francis turbine, you see these are the runners of the Francis turbine. These are the shape is little bit complex as compared to the runner of a Pelton wheel. Now, see the fluid flows in this direction. This is the direction of the fluid flow. That fluid enters like this and then flows within the blade passage. So, at inlet the flow is mainly have components in radial direction and tangential direction, but while it comes out of the runner, the flow becomes purely radial. I will be telling the reason behind it, and at the same time the passage is a converging passage. And as the flow takes place through the runner, the tangential and radial flow ultimately is being converted to a radial flow, and the flow area, the cross sectional area of the flow converges, and this is the height of the runner blade. So, flow takes place like this. If we consider this as the horizontal plane, is a vertical shaft, Francis runner, the flow takes place like that. So, at the outlet of the runner, the flow becomes purely radial and then it takes a 90-degree turn, and in the vertical plane, that is the parallel to the axis of this shaft, that is the axial direction, it is bent. That means, this takes a 90-degree bend and then it flows through the draft tube to the tail race. Now, at the exit of the runner, the flow has to be radial because of the two things. One is that the runner, as you know, the discharge from the runner is a waste through the, though we have a draft tube which reduces further the kinetic energy, but kinetic energy at the runner also has to be kept minimum. At the same time, we have seen that the cavitation not to occur, the velocity at the runner inlet, if you see at the runner outlet or inlet to the draft tube has to be low. If you see the earlier equations, then you will see there is likelihood of cavitation if the velocity at the inlet of the draft tube or at the runner outlet is high. So, therefore, to keep the velocity as minimum as possible at the runner outlet, to keep the kinetic energy out the outlet minimum, and also to avoid cavitation, we design the blade in such a way that the fluid velocity becomes minimum, and that can be achieved provided the velocity becomes purely radial. That means, the absolute velocity is in the direction of the radius, becomes radial. There is no tangential component of the absolute velocity of the fluid at the runner outlet. So, runner is designed this way. So, with this concept in the background, let us draw a Francis runner blade. That means, if this blade, this is the blade and this is the height, for example, the height of the blade, which also varies from inlet to outlet. I will explain afterwards that this increases from inlet to outlet, the height of the blade. However, if this is the height of the blade, that means, if we take a cross sectional view like this from the top, if we see the blade, well, the flow enters at a higher radius, radial location and comes out the lower radial location, and if we take the sectional view from the top, a blade looks like this. A blade looks like this. If you see a blade This is the typical blade shape, and this direction is the tangential direction. Tangential direction, tangential direction, tangential direction. Okay. That means this is the direction of the rotor speed u. Now, let me first draw the velocity triangle at the outlet. So, the radial velocity will be gliding along this, will be having the same angle as that of the blade at the outlet, and as I have told, the outlet velocity will be purely radial. There will be no tangential component. This is V2, and if this is V2, so this is VR2 and this is U2. 2 is the section at the outlet, and this velocity triangle I told you earlier that VR2 is nothing but the difference between V2 and U2. Therefore, V2 is VR2 plus U2. So, VR2 plus U2 gives you the V2, and V2 is purely radial. It does not have any tangential component of velocity, and it can be written as equal to Vf2. This is the nomenclature we use for the radial component of flow velocity, which is known as velocity of flow, Vf2. Now, at the inlet, the diagram will be like this. This is the again coinciding here. Another thing I like to tell you, that the angle the relative velocity makes with the tangential direction, let it be beta 2, which is the blade angle at the outlet. Similarly, one can draw the velocity diagram at the inlet like this. This is U2, this is U1, this is VR1, rather VR1, and this is V1. Okay. Here also, if you write, you will see that VR1 is equal to V1 minus U1. So, that V1 U1 plus VR1 is V1, U1 plus VR1 this way. Now, this angle we define, or this angle whatever you call, if this angle is defined as the angle beta 1, that is the angle at the inlet of the runner at the inlet, that is the angle of the relative velocity at the inlet, and the angle which the absolute velocity at the inlet makes, the nomenclature usually given alpha, alpha 1, where alpha 2 is 0 in this case at the outlet, that is the velocity, absolute velocity makes with the tangential direction. This is the tangential direction, is nothing but the angle of the guide blade, because the guide blade directs the fluid to the runner. So, from the guide blade, the fluid velocity relative to the guide blade means guide blade or guide vanes are static. So, therefore, this is the absolute velocity, this is the angle of the guide vane, and here we have a flow component of velocity. So, VR1, this velocity is, this is Vf1, and this one is therefore, Vw1, that means the tangential component of the inlet velocity V1. The outlet velocity tangential component is 0, here Vw2 is 0. Okay. This is the nomenclature for the velocity triangles or the velocity vector diagram at the inlet and outlet of a Francis turbine. Now, here two things are very important. Francis turbine inlet is having a velocity which has substantial tangential and radial component of velocity. As it flows through the turbines, the flow is mostly in tangential and radial direction, but at the outlet the tangential component reduces to almost 0 and the flow comes in a purely radial direction, that is absolute velocity direction is radial, that is perpendicular to the tangential direction. This has no component in the tangential direction. So, this is the diagram. Now, let us find out the value of in a head per energy per unit mass, not head. Head is energy per unit weight, unnecessarily I am not using this G. So, energy per unit mass that is being delivered to this runner by the fluid as it passes through it. So, this we know is given by V, we use this Euler turbine equation VW2 U2. Since in this case this is 0, this becomes VW1 U1. Achha, here one thing you have to remember, that U1 is given by, what is U1? U1 is given by ND1, pi ND1, sorry, 1 pi will be there, and U2 will be given by pi ND2. Okay? Since D1 is more than D2 and N is constant, U1 is always higher than U2. So, while drawing this vector diagram, one has to take care of that U1 should appear bigger than U2. That is just for a sense. Now, therefore, VW1 U1. Now, VW1 can be expressed, now little bit trigonometry, the fluid mechanics concept ends here. Now, little bit trigonometry afterwards, the VW1 is VF1 cot alpha 1, VF1 cot alpha 1, well, and U1 can be written as, that is VW1 minus this one. VW1 is VF1 cot alpha 1, that means this one minus this one, this is VF1 cot this angle 180 degree minus beta 1. So, if we denote this obtuse angle as beta 1, it will be plus VF1 cot 180 degree minus beta 1, which is minus sorry, which is minus. So, minus minus, this will be plus. So, this will be cot alpha 1 plus cot beta 1. So, this is U1. U1 can be expressed from this trigonometry, triangle geometry, U1 like that, VW1 like that. So, therefore, we can write E by M is equal to VF1 square cot alpha 1 into cot alpha 1 plus cot beta 1, cot alpha 1 plus cot beta 1, that is the energy per unit mass. This we can denote as small e, that is being delivered, that is VF1 square cot alpha 1 into cot alpha 1 plus cot beta 1. This is the head, not head, energy per unit mass, head is energy per unit weight delivered, VF1 square cot alpha 1 plus cot beta 1. Now, here we define a blade efficiency eta B as this energy delivered, that means this energy delivered to the rotor divided by the input energy. Now, here input energy is not the kinetic energy, that is the concept. Earlier in Pelton wheel, the input energy to the runner or the rotor is the kinetic energy of the fluid, because pressure throughout was the same, that was the atmospheric pressure. But here there is also a pressure energy or the static head which changes during in course of its flow. So, therefore, we cannot find out straight away from that concept that V1 square by 2. So, we have to know the pressure energy or pressure head or static head at the inlet to this runner. So, this is rather expressed in this way. This is the energy per unit mass delivered plus the energy which is lost here, that is V2, V2 square by 2, that is related to V2, that means V2 square by 2. And since V2 is equal to VF2, I can write VF2 square by 2. That means this is what? This is this energy delivered to them, and this is the energy lost or energy given out or discharged from the runner. So, this energy is added to get the input energy. Okay. So, the input energy has to be found from this equation. So, if you do that, Now, if you write that, then and if you just put this value, you get eta b equals to, now if I write Vf 2 square first plus 2 Vf 1 square cot alpha 1, this one cot alpha 1 plus cot beta 1, that means 2 e plus Vf square, numerator will be 2 e, that means 2 Vf 1 square cot alpha 1 cot alpha 1 plus cot beta 1. Well, now another concept here we have to take, that in this type of reaction turbine, Francis turbine, Vf1, that is the flow velocity at inlet, is equal to the Vf2. So, the flow velocity at inlet and outlet is made same and they are made uniform, the flow velocity. If we assume this Vf1 and Vf2, so that the change of momentum in the radial direction is 0. So, to have this, the flow velocity in the radial direction, that means Vf1 and Vf2 are kept same. So, if we substitute this Vf1 is equal to Vf2, then this will be cancelled out, and if you make a little rearrangement, then we can write eta b as 1 minus 1 by, just a rearrangement, 1 plus 2 simple rearrangement cot alpha 1 cot alpha 1 plus cot beta 1. Well, so this is the final expression of the blade velocity in terms of the guide vane angle and the blade angle at the inlet, 1 by 1 minus 1 by this. So, it is not necessary that you have to remember this formula at all, no need, but you must know how the things are being derived and the concept that is used for defining this thing. Blade efficiency means the runner efficiency, the wheel efficiency. So, here we use the energy delivered to the wheel from the Euler's turbine equation, or the runner divided by the energy input at the runner, which is found by output plus the loss in the form of the kinetic energy at the outlet. So, this way we find out this eta, because here we cannot simply use the kinetic energy at the inlet, because with respect to the outlet, the pressure energy or static head is higher at the inlet. So, this change has to be taken into account along with the kinetic energy, which is manifested through this. Here is only the concept. Afterwards, some trigonometric and algebraic manipulation gives you this value. Now, usually the value of beta, that means beta 1, that means the angle of the relative velocity at the inlet or the blade angle at the inlet lies between 45 degree to 120 degree. The value of the guide vane is lying between 10 degree to 40 degree. Now, another important concept is that since Vf1 is Vf2, now we can write Vf1 is pi d1 b1 equals to pi d2 b2. Now, what is b2? b1, b2 are the width of the runner or the height of the runner. This is depending upon its configuration. For a vertical shaft runner, this b is the height of the runner, and pi d b represents the flow area. Let us see this way, that here this is a runner. Let us consider this is a horizontal plane, this is the runner blade. So, this height is b. So, flow velocity, that normal area to the flow velocity is pi d times this height. Okay. So, d into b, therefore, in case of a turbine whose shaft is horizontal, turbine is in a vertical plane, this b is the width. So, pi d b represents the flow area, pi d1 b1 is flow area, that is the area, cross sectional area normal to flow velocity at inlet and that at outlet. So, Vf1 is this, I am sorry, and Vf2 is pi d2 B2. First line we should not write this, since Vf1 is Vf2. So, pi d1 B1 is equal to pi d2 B2. So, therefore, d1 B1 is equal to d2 B2. Now, since d1 diameter at the inlet is higher than d2, so B1 is smaller than B2. That means, the width or height goes on increasing in the direction of flow. That means, from inlet to outlet. That means, if you just think the height of the runner is small here and it goes on increasing at the outlet. So, that the flow velocity remains same. To make the flow velocity remain same, flow velocity is not this, actually it is q dot by this, q dot by this, I am sorry, q dot by this pi d1 b1, I can write separately, that is why this problem is there. Q dot can be written as Vf1 into pi d1 b1 separately, q dot is same written as Vf2 pi d2 b2. Q dot is same because the flow is steady, and if we consider Vf1, Vf2 are same, then the conclusion is d1 b1 is d2 b2. That means, the width or height, sorry, not this one, increases from inlet to outlet, because inlet d1 is greater than d2, it is radially inward flow. That means, the inlet diameter is more than the outlet diameter. So, therefore, inlet width or height is less than that at the outlet. So, this is the concept for this geometry, and usually the value of B by D at the inlet B1 by D1 is kept at between 0.6 to 0.66. Okay. Now, next we will see, we will derive the expression of specific speed of such a runner. Similar way as we did for Pelton wheel, specific speed for the turbine, let us write as n p to the power half h to the power 5 by 4. Now, P can be written as rho q dot g h in terms of the hydraulic efficiency. So, this is the head available, flow rate rho g and h is the head available. That means, this is the total power available times the hydraulic efficiency is the power delivered. Okay. Total head available multiplied with the mass flow rate into hydraulic, the way we did earlier. So, if you now put this there, then what we get? We get n p half, we get n rho q dot g h eta h half, and h, if you just cut eta h half, this h and this h you write h half h 5 by 4, that means h minus 3 by 4. H to the power half minus h to the power 5 by 4, I write like this. Now, if you write n as u1 by pi d1, where u1 is the blade velocity or runner velocity at inlet and d1 is the diameter at the inlet. Again, we have u1, we found out from the trigonometric relation Vf1 cot alpha 1 plus cot beta 1. Okay. So, therefore, we can write n as, just substituting this Vf1 cot alpha 1 plus cot beta 1 divided by pi d1. So, this is the value of n. Now, if we have, now before substituting the, we have to find out the value of h. Now, we know gh already, E plus V. How do you know that? Because earlier we told that the energy per unit mass that is supplied to the fluid or available to the turbine or available to the turbine by the fluid. By definition, this is the H, that is in terms of head. So, GH is E plus Vf2 square by 2, then H is equal to 1 by G E plus Vf2 square by 2, and this becomes 1 by G. Already we know these things. What is this? Vf1 square by 2, we can take common 1 by G Vf1 square by 2 into 1 plus 2 cot alpha 1 into cot alpha 1 plus cot beta 1. This you can make a second bracket, and this is third bracket. So, this is 1 by G. E is also Vf1 square by 2 plus, that is already we have taken Vf2 square is equal to Vf, here we have used Vf2 is Vf1. So, this we have taken common 1 plus the E is Vf square by 2 into cot alpha 1 into cot alpha 1 plus cot beta 1, already we derived earlier, and Vf2 is equal to Vf1. So, take Vf1 square common and then it becomes this. And if you put this value of H and this value of N finally in this expression of NST, then you get an expression like this. NST is equal to, if you put this value, then you get an expression. I write here separately, you just see it, there is nothing great. If you do, you will get it. It is simple algebra. 2 to the power 3 by 4, G to the power 5 by 4, rho eta H in terms of q dot half divided by pi d1, Vf1 to the power minus half, cot alpha 1 plus cot beta 1 into 1 plus 2 cot alpha 1 plus cot beta 1 to the power minus 3 by 4. There is no need of remembering this formula, but this is the way this has been derived, one must know. And Vf1 is equal to q by pi d1 b1. One can, this is Vf1 q half minus half, that means this can be taken together as q dot by Vf1 to the power half, and q dot by Vf1 can be replaced as pi d1 b1, and another expression will come. So, this way one can express the specific speed in terms of inlet guide vane angles and the inlet blade angles. Usually these things are known: rho, the hydraulic efficiency of the turbine. For a given flow rate, this depends upon this diameter of the rotor and this alpha 1 beta 1. Diameter means diameter at the inlet, diameter of the rotor, no, this is diameter of the runner blade at the inlet, alpha 1 and beta 1. Now, the value of the specific speed usually lies between 50 to 400. Again I tell you, the meaning of this is the Francis turbine works most efficiently within this range of specific speeds, and the values of alpha 1, beta 1 and the values of B by D at the inlet already has been told earlier. So, with these values, if you put here, the NST will come as 50 to 400, but if you choose a value of D1, otherwise if we know the specific speed, we can find out the value of D1. So, this is one guiding equation for designing the turbine for a given specific speed. Actually, specific speed we have to know for which we are going to design this turbine. Turbine is suitable for this specific speed, which is much higher than that of the Pelton wheel. That means, this is for relatively lower head as compared to that of a Pelton wheel. Okay, thank you.